Good morning. Today I am going to talk about signals and systems. So this course is mainly divided into 5 modules. So first module it is having the introduction to signal, second module introduction to LTI system, module 3 transform analysis of continuous time signal, fourth module transform analysis of discrete time signals, and module 5 applications of transform. So my name is Dr. Parnasree Chakraborty. I am Associate Professor in EC Department, BSA Crescent Institute of Science and Technology. So here the main outcome of the course is to represent the signals, various type of signals mathematically, to evaluate and manipulate the signals mathematically, then to characterize, identify the LTI systems, and to apply various transforms like Fourier transform, Laplace transform, Z transforms, etc. for solving various signal processing problems. And the last one is the synthesize and discrete time system from basic component blocks. So now here these are the course outcome. And next we are going to see the textbook. So textbook mainly for signals and system, I am going to use this Oppenheim textbook as well as Simon Hakin. These two are the standard books for signals and systems. So coming to the module 1, that is introduction to signals. So here basically in this module, time domain representation of discrete and continuous signal will be covered here. Then various standard elementary signals and complex signals will be analyzed here. Then basic time domain operations on signals. Then various type of signals, their energy and power calculation. Then finding the correlation of signals, signal classification and its symmetry, periodicity of discrete time signals, and synthesis of simple signals will be analyzed in this module. So before going to the content of the module, let us first try to understand the terms signals, systems, etc. So here this diagram, it shows a system where the input is signal here. So I call that as an input signal, which is applied to the system. So that means the system is going to perform some kind of operation on this input signal so that it is giving another signal which is termed as output signal. So system is basically going to perform operation on signals. So what is signal? For example, here it is shown an analog signal or continuous signal whose amplitude is varying with respect to time. Now this system may perform any kind of operation on the signal and it may produce the output signal, which is nothing but after operation by the system, the signal, input signal which is converted as output signal is shown here. So you can see that basically the input signal here, it is considered as time domain signal. That means the x-axis is time, y-axis amplitude. But this system, it is given the output which is a frequency domain version of the signal. That means in the x-axis it is frequency, y-axis amplitude. That means the system has converted the time domain signal into its frequency domain signal. So that is why here it is given that LTI system perform any kind of processing operation. In this case the operation is nothing but the conversion from time domain into frequency domain. So coming to the next, what is signal? So the definition of signal. So signal is one that carries information and is defined as a physical quantity that varies with time, space, or any other independent variable or variables. So example of signal may be considered as TV signal, radio signal, music, speech, image, etc. So here it is a signal which is a one-dimensional signal. It's an ECG signal, and on the right side it is an image signal which is two-dimensional biological signal. So here signals can be 1D, it can be 2D, it can be multi-dimensional also. Coming to here classification of signals, We are having various classification like continuous signal, discrete signal, periodic signal, aperiodic signal, energy signal, power signal, even signal, odd signal, sinusoidal signal or complex exponential signal, causal or non-causal signal, deterministic signal and random signal. So one by one I will be discussing here. So let us first try to understand what is continuous signal and what is discrete signal. So continuous signal, as the name suggests here, continuous, that means the signal is continuous with respect to time, its amplitude is continuous. You can see here on the x-axis it is time, y-axis it is amplitude. So at each and every instant of time the signal is having some amplitude value here which is not undefined. So this kind of signal is called as continuous signal, which is depicted or denoted by x of t and shown in the figure 1. So here at various instant of time, any instant of time, the signal amplitude is continuous. Okay, it's continuous or the amplitude is also continuous. Time is continuous. Here amplitude is also continuous. Coming to the discrete signal, you can see here. So here the time is considered as 1, 2, etc. It's an integer value. Time instant, various time instant which is considered as 0, 1, 2, 3, etc. At that point the signal is having some amplitude, whereas in between that 0 and 1 or 1 and 2 the signal value is undefined. So this kind of signal is called as discrete time signal. Another type of signal is called as digital signal, which is represented only by two amplitude, that is 1 and 0. So the amplitude is either 1 or it is 0. That kind of signal is called as digital signal. Now here this is A to D conversion or analog to digital conversion. So what is here? The analog signal is first given to a sampler. The sampler will perform sampling. So at various time instant we are going to collect the samples. Those samples are quantized, and after quantization the truncated or rounded off values of the signal is considered and it is encoded as ones and zeros, which is nothing but the digital, which is explained here with the help of this example by considering this time domain signal, analog sinusoidal signal, whose various amplitudes are considered here. Sampled version, that is this sampled values, various time instant. Then quantized values are also written, and with respect to the quantized values, the encoded values are written here. So basic signals, so basic or the elementary signals, here some few signals are given here as example. These signals are nothing but the basic blocks of any other signals. For example, if we know these elementary signals, using the concept of this signal, any signal can be constructed. So now I am going to talk about the basic elementary signal or the standard signals. These signals are the standard or the elementary signal. So using these basic signals, any other signals can be easily constructed for any purpose. So what are those standard or elementary signals are? They are delta signal or a unit impulse signal, or it may be step signal, ramp signal, sinusoidal signal, exponential signal, and many more are there. But to list a few, I have taken only 5 elementary signals here. So once we understand these signals properly, using the concept of this signal, we can construct any other signal. So let us now see the delta signal or the unit impulse signal. So delta signal is nothing but here. So this is the continuous time delta signal and discrete time delta signal. So it will be better if I explain the discrete time delta signal. So here you can see that the discrete signal means the time index n is integer. So when n value equal to 0, the value of the amplitude of the signal is 1, and the signal is denoted by delta of n. So this is the unit that is unit sample sequence or the delta sequence whose value is equal to 1 when n equal to 0. Its value equal to 0 when n is not equal to 0. This kind of signal is called as delta signal. So this is the way we can represent a delta signal. We can write delta of n in the sequence representation also. So this is the graphical representation, this is the equation representation, and this is the sequence representation of delta signal or unit impulse signal, or we call that as unit sample sequence. Coming to the, so here there is an example how to sketch. So for example, if the signal is given here as 2, 3, minus 8, 5, minus 1. So this signal, any signal can be represented with the help of delta signal. So that means this arrow, the arrow shows that the signal, this sample present at n equal to 0. So at n equal to 0, there is a presence of delta signal multiplied by 2. So it is at 0, the value is 2. At n equal to 1, the value is 3. At n equal to 3, the value is minus 8. And at n equal to 4, the value is 5. And n equal to 5, 0, 1, 2, 3, 4. So n equal to 4, the value is minus 1. So this is the way, that is another signal x of n, which can be represented with the help of delta signal. So there are many examples, we can try it. Coming to the next variety, that is unit step signal. So unit step signal, the definition is given here. This is the graphical representation. It's denoted by u of t. So u of t is equal to 1 when t is greater than or equal to 0, equal to 0 when t is less than 0. T is less than 0 means this here the left hand side, that is the x-axis left hand side, we want to mean this, its value equal to 0, and from t equal to 0 to t greater than or equal to 0, that is the right hand side of the x-axis, its value is equal to 1, and it is shown in the figure. Similarly, the discrete time unit step signal is shown here. Coming to ramp signal, the graphical representation of the signal is given here. It is denoted by r of t. In equation representation, we can write r of t is equal to t when t is greater than or equal to 0 and 0 when t is less than 0. Similarly, we can denote the discrete version of the same signal, which is shown here in this figure. Okay, and then coming to the sinusoidal signal, the fourth variety. So here we know that the sinusoidal signal, this is the representation technique. We can write x of t as a sine or cos omega t plus phi, where omega is nothing but here 2 pi f. Okay, here 2 pi by t. Also omega can be represented by 2 pi by t because f is 1 by t, and then f is nothing but the frequency, a is the amplitude, and phi is nothing but the phase here. Okay, so if we want to write the sinusoidal signal, we can write in terms of sine or we can write in terms of cos. Okay, inside that omega is nothing but representing the function of frequency, and phi is nothing but the phase. The sketch of the signal is also provided here. So this is the discrete time sinusoidal signal. And coming to the exponential signal here, exponential signal can be represented by using this equation. X of t is a is nothing but the amplitude. So exponential can be written as e power at. So based on that a value, the signals are represented here. So if a equal to 0, that means it is a DC signal. If a is positive value, that means it is a growing exponential signal. And if the small a, e power small a is a negative value, then it is a decaying exponential signal. So these are the 5 different basic or the elementary signal. So using the concept of this signal, any other signal can be easily constructed. So here again, now next thing in this module we are going to see as basic signal operations. So the signal operations are divided into 2 parts. The one part is based on the amplitude, that is few operations are done based on the amplitude and few operations are done using the time. Based on that, the total basic signal operations can be classified in this way. So amplitude wise operations are amplitude scaling, signal addition, signal subtraction, signal multiplication, whereas time domain operations can be time shifting, time scaling and time reversal. So let us see one by one. So what is amplitude scaling? So here it is given with the help of one example. So amplitude scaling, that means we are not going to perform any operation in the x-axis. The operations all will be performed on the y-axis. So here x of t, a basic signal is taken here, which is from -1 to 1, the signal, its amplitude is 2. Suppose now I want to have an amplitude scaled version of x of t. Say it is 2x of t, that means I am going to scale x of t's amplitude by 2. Now previously amplitude was 2, is multiplied with 2, I will be getting here as amplitude 4. There is no change in the time. Time is from -1 to 1. Here also it is from -1 to 1. Only the amplitude is changed here from 2 to 4 here, because it is 2x of t. Right? Now we want to do amplitude scaling by a fractional value, that is 0.5. That means previously here the original signal had the amplitude equal to 2. Now it is multiplied by 0.5. So 2 into 0.5 is 1. So the amplitude is changed to 1, whereas the time did not change. It is from -1 to 1 because it is only amplitude scaling, no time operation. Coming to the addition here. So in this case we can explain it better with the help of this example, where two signals are taken, x1 and x2, and if they are added here, suppose x1 and x2 is added to get the signal z of t, then how the signal z of t will look like. So here it is as simple as given here. We need to consider the time, which is not changed here. The total time is from -10 to 10 in between these two signal. The maximum time is -10 and minimum time is -10 and maximum is 10 here. So from -10 to -3, there only this signal is existing, x2 is existing. So -10 to -3 only x2 is existing, whose amplitude 2, and from -3 to 3 both the signals amplitude to be added. So this signal is amplitude having 2, this having 1, 2 plus 1 is 3. That will be from -3 to 3, whereas again from 3 to 10, this x1 signal amplitude is 0, whereas x2 signal will be retained here. So this is very simple. Like as we perform the general normal addition, we are also going to do the addition here in the amplitude or in the y-axis, where x-axis values are not changed here. Okay.